Hello everyone. Welcome to the Rust Meetup. March. Today we'll be having the Rust Meetup March, and for those people that is live, you can switch to the Discord channel. You can post questions in chat, or you can wait until the event is over. Then you can ask the question. The topic of the day is about trades. But before I start, I'll be hosting today. Before I start, I'll be giving some news on Rust. What happened before this? And yeah, so since the last meetup, they announced Rust 1.59. And the interesting thing is that they released the inline assembly. So it's stabilized now, and you can do the inline assembly with using the macro ASM macro. And you can also do the destructuring assignments. Previously, you can do destructuring, but you need to put let in the front. But now you can assign to the values here. So there's the new interesting stuff that is being released for the last release. You would say major release. Now let me switch to the other screen. For the participants, if you have any questions, feel free to just post in the chat, or you can just ask during the just ask in the Discord. Yeah, I'll reply there. As part of it, originally the plan was to talk about Rust traits and static dynamic dispatch, but I think just Rust trait enough will be enough. And the examples on the slides given below will be structured in the story form to show like why and how, why is there Rust traits. That's just based on my own findings, and some I just took from the Rust book and some other reference like RFC. So what is Rust trait? Rust trait is like similar to like the class and something, not very similar, but it's something like that. And you can know it easily in Chinese. Mandarin you call 特征, and it's like characteristic, like, so it describes how something behaves. The word in English, they call it trait, but it's less commonly used. So the Chinese word is easier to understand. They call 特征. And you can also consider it as part of OOP. OOP is object-oriented programming. But in this case, Rust trait don't do the inheritance. It does composition. Inheritance is like you have one class inherit from another class, and it inherits all the data. But composition is more like you only define the functions it have, and you can have multiple traits for one item. And there is as like the other composition, usually there's for Rust trait there's no data, so there's only methods, or some of other languages they call it contracts. So it's like the public behavior of how that function interacts with other functions. And for Rust trait, it's also integrated with the rest of the system, like unsafe, generic, lifetime, type inference. We might discuss a few of this within the talk. And trait must be in scope to be able to call its method. This is just one of the behavior of Rust trait, such that if the trait is out of scope, then you can't really call it method. Later we'll talk about that. So let's talk about why a trait is needed. So there's a story of two concepts of opposing force. Like one is called yin and one is called yang. I think they are also called material energy. So there's one structure called yin and one structure called yang. So this is called a unit struct in Rust, where it's a unit and it's also a struct. So you can think of it just like one variable or structure or something like that. But it's a structure, but it's empty or something. And so both of them implement the same function. IMPL is like more of a syntactic sugar, but IMPL yin means that yin have these are all methods under yin. So yin has its light function, so this is called a method. So this function will output a boolean false. So if you do yin colon is light, then it will return false. And so this is returned, but for those not familiar with Rust, the last item inside the block, like this is the block. So the last item inside will be the return. Or within any expression, basically the last item will return out of the scope. So this will be returned out of the function. So this will be returned false, and this will be returned true. So yang is like is true. And then that comes, then you need to do a function to check if an item is light. So okay, so then we do is light. And what this is a function, fn is like a function, and this parameter is like this is just the variable name. I just add the underscore in front to silence the compiler. And impl fn bool means this is a variable of a function with no arguments and returns a bool. So basically the same. You see basically the same thing here. But IMPL here means something that implements this, and it returns nothing. Basically, you see it's nothing here. So you can think of it like a generic function or something like that. But this is not. There's no generics involved here. Then when you run, so in Rust, when you want to run something, you need to put fn main. This will be the function you run. So like this will be the function you run in the file. Then it's like, so this works. This compiles. And as we know, everything will change. And now we need to have another function called is1. Just now we have is light, so means that got the light. And then now we have another function called is1, and then we implement the same thing. As we know, if you know about this, you might have heard is1 yin is 0. That's what I heard. So I put is 0 false, and yang is 1 true. Okay. And then and we have to create another function is1 here. Is1. Then we need to do this. You notice that if we do this right, it's very hard to differentiate. In IMPL fn bool, it's very hard to differentiate this and this. So is1, then I pass in yin is 1. But I could have passed in yin is light. If I pass in yin is light is false, is 1 false. Okay, this is lucky because both of them return the same output. But then there's no guarantee that we pass in the wrong function here, and then it does something, it does wrongly. So as we notice that if the function becomes more complicated, what if now we need to have a more complicated function that takes in both the previous function? Let's say we have a function that is called is yang, and the first parameter is whether or not it gets a it gets a function that returns whether it's light or not, and another is a function to returns is 1 or not. So we need to put in young is light and young is 1 here. And then, okay, you notice that if we have more parameters, then it's getting harder to track. So what if we could do something that can represent all of them? Then, so that's why we have traits. So traits to rescue. So what is traits for? Traits is to define the shared behavior. So both of them can be grouped under something we can call it energy. So the energy have we can define energy must have these 2 functions. One function is light and another function is 1. So but you notice that it's a bit different because for a trait we must always put in this the first parameter as self. Basically, this is also a syntactic sugar. This means let's so basically this syntactic sugar means that it takes in self as energy. Basically this is a syntactic sugar for this. Basically these 2 is the same thing. You don't worry about if for those new to Rust, don't worry about the ampersand. It means getting the reference. So it means we won't be discussing about the ownership and reference. We discussed it previously now. So now we won't be discussing about this. So this is just a reference. You will take a reference of energy and return this. And then, so now instead of IMPL yin, we can say IMPL energy for yin. So we are implementing this trait energy. We are implementing this trait energy for yin. So we need to put in all the items, all the methods within energy. So if you see IMPL something, it means that the item will contain all the methods within this trait. So in this case, it have is light and it will have also is 1. I simplify it. I just show one of them, but need to have all of them. And then we notice that the previous function will also break due to self. But yeah, that's not that important. And then so now we will change. Instead of writing it previously, we put in the currently. You notice just now we need to pass in 2 parameters. But in this case, we just pass in energy and then something that implements this energy because it implements the trait. So because yin implements the energy, because it implements the energy, so you can call directly. You can call energy dot is light within here because the energy is here, and the is light is within the trait, so you can call it. So this is how you want to guarantee that something, how you want to do the shared behavior. So if you have multiple items that have the same behavior, you can implement it as a trait. But sometimes you also want it to split into multiple traits. So a single item could have different behavior. Because things change, sometimes you need to create new traits. Yeah, so this is traits. Is there any question up till here? Okay, if there's no question, then let's continue to the next slide. So now we'll be talking about extension trait. And Rust only allows the inherent methods to be defined on the type, where the type is defined. Same goes for the trait. What this means is that why yet? Okay, let's ignore this first. Okay, why if you want to extend the third party trait with more methods? Okay, I understand this now. Yeah, so this means that if your type is inside a crate is like a library in Rust, and then you can only implement the methods for that type within the crate that you own. You can't do it for other people. Like you cannot like just go in and modify other people's code like monkey patching or something like that. You can't do that in Rust, because like if you have a library and then someone just patch another library for you, then that will be very confusing. So Rust doesn't allow that. So the trait you can only change within your trait start. You can only change the stuff within your own crate. But what if you want to extend the third-party crate stuff to third-party trait with more methods? Let's say you have let's say Rust has the iterator trait. Yeah, you want to extend it with more stuff. So this is also known as extension trait, to extend another trait. For example, we want to extend the full trait from full crate. You see here, we have another crate called full. So we'll import this function, we'll use it. So this is a crate, full is a crate. And so now we define another, so we define this called full ext. This is a convention in Rust, it's created in an RFC, but people don't have to follow this, it's just a convention. Rust doesn't guarantee that this must be ext. So you want to extend this full crate. So you add in another fn bar then self. So now you can no, full is not crate here. Okay, sorry, full is not a crate, full is a struct. So you can implement the extension you just define in your crate to that struct. And then when you use the full, right, you can use the full inside the other module, inside the other file you have. You can just use this. So you import full ext, and then you can start using the new items. You can start using the new methods within that trait that you imported. So if you have full here, you can use the fn bar. So this is called extension traits. You extend the third-party stuff. You use a trait to extend third-party stuff. Any question up to here? Bit louder. Hello? Okay, is it better now? Okay, never mind. Let's continue. I think I increased my volume already now. So the next is default implementation. From the previous energy example, we only see the methods defined in the implementation. So we only see methods in the implementation. But what if we want to have a helper in a trace that depends on another method? Just like you see, like we have one function and two functions, but the functions don't depend on each other. So this example, we will have a function depends on each other. We'll see. But I'll give you the rough one first. It's not the. So now we have a trait called jumpable, and there are two methods. One is called jump, and then one is called double jump. So we have a struct Homo sapien. Homo sapien basically human scientific term. So I have got the name. So now we want to implement the trait for. We want to implement a trait for Homo sapien. Then we create the first function, jump, and then we will print I jump. But then you want to do another function, double jump. Then you want to run the same function twice, right? Then you just run it twice. But yeah, you just imagine if we have 10 struct, then we need to do this 10 times. You need to do a double jump, and then inside double jump, we need to run the self.jump twice. Just imagine we keep doing this many times. So it will be very how to say, very non-ergonomic. So that's why we got default implementation. And default implementation means that inside a thread, you just call another function in a thread. So in this case, you will see that this is the default, this is like the default way the thread behave if you don't define it. This is mainly used a lot in the Rust iterator. Let me switch a bit. Okay, so we see here. Okay, so we open up the documentation. So this is used a lot in here. So you see this is the Rust iterator documentation. And then if you look at the methods, and you see a lot of it is implemented. This required methods basically means that that's the only required method that you need to implement. There are many other methods. You see there are many other methods, but you see that they have a default implementation. Only this one you implement one thing, then everything else is done for you. So this is the power of default implementation. And let's switch it back. Yeah. So the default implementation, you just do this here, and then you can call the other stuff you define in the same thread. Basically, you do this, and then you define the struct. You just implement when you implement jumpable, you just implement the jump. Then you don't need to implement the double jump. Then you can use the, but when you do Homo sapien, then you can just run double jump like normal. And then when you run double jump, it will do this. Of course, you can still override it manually. You want to change this to what you want, also can. Then it will not use the default. So this is the default implementation for thread. Okay, until now, any question? No. Next is thread bounds. So thread bounds is a bit more harder to understand compared to just the plain threads. So we need to understand, but thread bounds require some knowledge in generics. So we need to first explain the generics. What is generics? So some of the participants may not be familiar with it if you don't use some of the type language. So I'll explain the quick generics recap on like why generics exist. Let's say we have a function that returns one item or the other. So we have a function called ran. Basically, it's not ran. It's random. It's not random enough. It's just true. But the first argument is x is usize. Usize in Rust means unsigned integer, but of the machine size. This is basically like uint in C, the unsigned integer size, but based on your machine. So if your machine is 64-bit, you get a 64-bit unsigned integer. Unsigned integer basically means that your integer cannot be negative. So this is, and then you got two parameters. So two of them, you return one of them. Okay, now understand this. It returns one of them. But what if we need another version and different type? So now we have a string, and then we have another string. But you notice that it have the same function name. Then you'll get a compiler error. So Rust will error. This should be colored, but compiler will color it, but I don't have color here. So Rust will error because the same function is defined twice. You see, Rust error will say the ran is defined multiple times. First time in line 1 and second time in line 9. See, it's same function, but it has a different value. But this one, Rust didn't give a good suggestion to say, you need to use generic. It didn't tell you because, yeah, you can just use generic. And then in languages that don't have generics, but people still want to do generics. People still want to do something like that. So people will do like templating. They'll copy the code and then paste it one version, and then copy the code in another version and paste another version. And then this one will be so people will prefix this with usually what people do for the language that don't have generics. So they'll just do another function themselves. They'll manually duplicate the code and do this. But yeah, generics have good and bad, but it will save the number of typing user people have. But in this way, it's more explicit. You know what function will be there. So basically, you have two functions. Then this one will compile now because you have two different function names. So basically, generics hit is to do this. So you can say for ren, for anything of type t, so you have a generic of type t. And then, so x is of type t and y is of type t, and it will return type t. It means that your argument, the first argument type and the second argument type must be the same as the return type in this case. So basically, you see, you save the code from this to this. So this is for the generics. Okay, let's get back to trade bound. So we learned about the generics and why generics is required. Oh, wait, I'm still showing my browser. Oh wait, I should have shared my. I already shared my terminal. No. Okay, let me stop. Okay, let's get back. And yeah, I switch. Okay, let's go back. So go back to trade bounds. Just that there's generics. We learned about generics, so there's a function called ren. So ren takes in the first argument as U size. Just now I explained the U size is unsigned integer with the machine size. And second argument U size. Then it returns one of them. So it returns one of them. So it basically returns U size. And then so we need to have another version, but we have a parameter string. Second parameter is also string. So it returns one of them. But if we have both of these together, then we will see an error because they are the same function name. So people start doing this. People duplicate the function name and then add stuff to the function name. So it will start compiling because the function name is different. And for different type, people use different function. And generics, we can do this. We can just have a same one function, but it can do multiple items. Okay, let's get back to trade bounds. So we learned about generics, and now we have a trade in because we learned about the trade in parameter. We won't work. Like if you want to do the same example just now, this one won't work here because we do something that implements a trade called full. And we have another thing that implements a trade called full. But we return something called full. This won't compile because it could be different. Like your x could be bar, like let's say bar and bus implement full. So your first argument could be bar and second argument could be bus. And it returns a different one. So Rust doesn't allow it to compile because it must be the same. It must know what is the type beforehand. But this will work, just that you cannot. This will work, but it might not be the behavior you want, because what we want is we want the first argument and second argument to be of the same type, and the return type should also be the same type. And then, so what if we need generics, but we still want to limit the item? So this is for trait bounds. It means that it's a generic, but it is bounded by the trait. So let's take back the previous example, ran, but in this case, we put the full trait here. So it means that for the type within here, for the type T, it must implement the full trait. So for this, you can guarantee that the function implements the full trait. So inside here, you can use whatever method defined in full. So you can, like, let's say full have a dot bar, so you can use dot bar here, dot bar method. You can also do more generics. You can also add more stuff here like this, or you can also make one generic. You can also make one generic depend on another one. The same method is also used to define lifetime, but I won't talk about lifetime now. And this will guarantee that, it will guarantee that everything inside here implements full. Okay, and if we need more restriction, we can always make it stricter. So for T now, it needs to implement both full and implement bar. But if you want to do the thing we want to do previously, you can also do like this, implement impl full plus bar. You can also do. But so we discussed about the trait bounds. Basically, used for generics, you can define the behavior of the generic. And now let's talk about super trait. So super trait is sort of an inheritance for trait. So let's say, what if you want to have a trait that depends on another trait? Let's say we want to have a bar to depends on full. No, we want to have bus to run full twice the trait. Okay, no, this is outdated. But yeah, basically we have an example here. We have a trait called runnable, which means that anything in implements runnable can have a method called run. And then we also have another trait called Naruto runnable. Of course, we can also put a plus here. We can do what we learned previously. We can do the plus, so it means that it implements multiple items here. But yeah, I just show this for now. So this is a super trait. This trait must implement. So to have this trait, to implement this trait, you must implement this trait. So if you have something that have this trait, so you know that it also have this item. And then Naruto runnable have a method called Naruto run. So it will run, with the hands behind, two hands behind, like run and Naruto. Then, so now we create another function called go, and it is that takes in a parameter, the argument human, that implements Naruto runnable. So you basically have this Naruto run here. Now we do the same. We have a struct Naruto. How to have something that is this? To have this, we need to implement runnable for Naruto. You notice we don't need anything here because we already do a default here that does nothing. And we implement Naruto runnable also. But yeah, if you don't implement this, then Rust have an error saying that you can't implement this for Naruto because it doesn't implement this. So it's like a dependency. To get this, you must have this. This is used, from what I recall, this is used for there's a Rust trait called copy, and there's two Rust trait, copy and clone. From what I remember, the copy will have stuff in clone as well. So copy is a super trait of clone. If you can put more stuff here. So because this is easier to type it out. So n is node is h. So the hash takes in two node. And then hash will return a boolean. So it checks these two node and then return a boolean. But if you want to use it, it is quite inconvenient because if you want to do generics for it, it's quite inconvenient because we need to write out like so many types. You need to do so many generics here. Like we want to do G is graph NE. Because these two needs to be the same, you see? The N needs to be the same. So we need to pass in the N here. And then the G, you need to put the N here and E here. Because this is how the graph is defined. So every time we use the generic here, we need to specify, every time you use graph, we need to specify N and E. So we specify this. And if we can't just put N here because it won't like, you can't have it hanging by itself. So you need to define N here as well. So we need to define there's a generic called N and a generic called E. And then there's a G, which is bounded by, remember this is a trait bound. The G is bounded by graph with parameter N is the first generic here, N, and E is the second generic here, E. And you notice it'll get harder to read as this goes on. So the first parameter for this distance is graph, which is taking a reference of G, which is a graph. Second parameter is N. The start N is also node. So you can see here the N all is the same type. Yeah, this is also taking a reference of node. Start and end as well. So it will return and UINT. Okay, this is wrong. This is outdated. I took this from an older RFC. Probably they have UINT previously, but they changed it to use size. I think this is this older RFC. And so here then they introduce associated types. It means that we have an item, we have a type that is associated to the trait. See? So the graph will always have a type N and will always have a type E. But yeah, now we lose the generic. This is no longer generic because now one graph must be associated with only one type and one node type and one edge type. So you can't do, if you want to implement the graph for something, you can only implement one graph now. And if you implement one graph, then you can have the N and E here as specified during you implement. So when you implement, you just need to put out the type N equals to what the type you want to be. Then this N is taken from here. This N is taken from the generic N here. It can be any type you specify here. Later when you implement, you specify the type. So when you implement, you just specify the type. So now the N and E is associated to graph. See, this is more readable. When you So for the same function, distance, then there is a g, which is the graph, is the trait bound g here. So you see, we have no more n and e. This is easier to type out also, easier to read. And then you have the graph, which is the same as previous g. But now start, you just say that g, the item n within g. So this basically refers to, and then the n is the same. So this is associated type. It means that the type is associated to that trait. It just specifies the behavior. It's not like it just specifies the type only. It is not containing the data, just a type. And there are also defaults with the. You can also do defaults. Basically, you see just now, if you want the type to have a default, then you can always put equal to some default. But I won't show that now. And you can also do generic. What is it? Did someone say anything? Okay, never mind. So, and then there's also GAT, generic associated type, but this is not fully stabilized. There's only part of it. So as you can see, this is an example of GAT. There's a life, so you have a type, but this type now have a generic. It's not possible now. I'm not sure whether it is possible now or not, but the GAT is partially stabilized, so not all of the stuff within the generic associated type can be done, from what I recall. So this is what it looks like. You can specify basically this is a lifetime, how you specify lifetime in Rust. But I won't talk about lifetime here. Lifetime is basically how long a variable live, like basically a lifetime of the type. But here you can just think of it as a normal n, like a normal generic here. You can just think of it as generic, but here in the example they give is lifetime. So you can just think of this T, type T, and type T. So this is the use case of string generic associated type, where you can put generic within the associated type. So we have discussed generic. We have discussed generic type. So where we add the generics to the trait, and we also discussed associated type. Then some people might get confused, like, oh, there are two methods we can do the same trait. So when do we use one or the other? And if you see, associated type are used like when there's only one IMPL. Let's say there's an iterator, the trait iterator. This is in Rust standard library. So iterator is a trait to say how the structure will iterate over something. So in this case, you have a type item. So this type item means that when you call next on the iterator, so it means you get next item on the iterator, it will return you this item. So as you can see, iterator can only have exactly one item type. Otherwise, it will be confusing. Like you have the same iterator, but when you get the next value, you suddenly get a different iterator. That's why it is implemented as associated type and not generic type. So it cannot be generic because you want to have exactly one item. Like when you iterate over a string, you want to iterate over each characters within the string, then you get first character, second character, third character. Not like you get first character, then suddenly the next item you get 1 byte, then it will be confusing. So this is only must be one single type for the trait iterator. And from the Rust, I also take another example. So when is generic types used? So generic type is used when there are multiple types are needed. Let's say in Rust there's a trait called from iterator. It means that this thing can be derived from an iterator of the generics A. So you can have from iterator where the P is the generic, and then there's about basically the where here is similar to the trait bound you see just now, just that it's a different syntax, and you can put more stuff within here. You can like go next line with a different trait bound. Otherwise you have everything put in one of this this one, and then you make it very long. So this one will make it clearer. So we also have another example borrow, which is easier to understand, but I show this example because we have never seen this. So what this from iterator does is it will take in, and you have generic A, and here we have something that have iterator with so if for anything this T is anything that implements into iterator with the associated type of item is A. So for this basically means that anything that implements the into iterator implement for iterator. This is just basically doing the reverse. It's just reversing the into iterator. But yeah, for those that is not very familiar with Rust, the into iterator is you can make something an iterator, because this is just iterator, but iterator is something that it's a trait that say you can convert that item you have, the struct or enum or something, you can convert it into an iterator. That's basically it. And from iterator is similar, you just convert it back. But you also note that it can be mixed. You can also mix two. You can also use both associated type and generic together. So we have an add trait in Rust. So there's a trait called add. In Rust there's add trait because like you can have, let's say you have custom type, you can just implement the add trait. Then you can add two custom type together. Let's say you have a duration, you have a type duration type, and you have another duration type. Then you can add them together, then it will become a duration type. So in this case, you see the trait add with the RSH basically is the first generic here. Self means that by default the type is the same as itself. Basically, okay, let me show an example. Let's say you have a duration structure. I will show the stuff inside, but you can implement this add for. Okay, let me check it out. Yeah, you can do this. You can implement add for duration. Then you want to have type output. If you add duration with duration, what will it appear? It will appear as, okay, let's not use duration as the first example. Let's use date time. So yeah, so I don't give the values here. So you have a date time. Okay, no, use duration. Confused a bit. You can't really add date time with date time. So you add duration. By default, you see just now we have a self here. And basically this means duration by default. but we don't have to specify this because that's a default value, default to this, so it defaults to duration. And then the function, the output, if we add duration with duration, what will it become? It will become a duration. And we have an add function, we must implement this. So you'll notice here it doesn't have this thing because it's not taking by reference. It takes the whole value and use that value. So the value is gone. So the right hand side is basically the same thing. You can do duration here. Let's do this for now. But yeah, here we can always do this. You can always change this to self, because self means that it will get itself, because self means it is duration, but it's the same. I use this to make it clearer. So with this, you can, if you have this, then you can have duration. You can let's say you can have the duration A and duration B, and you can duration A add with duration B. You can do this. So this is adding a duration with duration. But what is the generic for? Like what is this generic? So what we can do here is we can have date time. You notice that I'll swap the position a bit, but just ignore that for add date time for duration. So you can do this. This will work because it's a different trait. By default, it's duration. So you notice that these two different traits, it will work. Because it implements two different stuff. One is add duration, one is add date time. So the output should be date time, because once you add the duration, it will be another time also. So basically here you have right hand side, you have date time, because this is here, it's mentioned here, RSH. See, RHS here is RHS here. So the output is date time. So once you add a duration with another date time, it will become a date time. So what you can do here is you can have a date time. Let's say you have a duration A and a date time B. And then, so now you can do this duration A plus date time B. This will work with this implementation. But you can't do this. You can't do date with that. You can't do date time B plus duration A. You can't do, because you add the right hand side the duration you add to right hand side must be date time. You see, the duration at the right hand side must be date time. So if your right hand side is, if you flip it, means you are wrong already. Then it will work. So this is basically like how you can mix both the generic and associated type. And next is I've discussed most of the stuff, and now we'll talk about some concerns with and the results. The trait with trait. So there are issues with trait, and then based on this issue, people also do some designs, and the design is slightly different. So one thing is auto-derived and ambiguity. It's a bit harder to understand this, but auto-derived is basically like Rust automatically figure out what type you want. It will infer what type you want. So if you have let's say if you have type A, it will figure out, you might want type B. So auto-derived, there's this, so there's ambiguity. Let's say you have a trait pilot called fly. And then you have another trait wizard, also have a method called method fly. Now you have a struct human. So for human, you implement pilot and you implement wizard. You see, there's only fly here. And then you notice that, the fly here. So one is pilot for human say, hey, this is your captain speaking, and the wizard say up. So both have the same function name, you know. So if you implement the human, and then you also implement the human, there's a function called fly, and it's waving. You just print here, waving arm furiously, and then then the compiler have error, so Rust doesn't know which trait to use, and then it says so this says type of notation needed, because you have when you print a baby dot animal baby name, so you call, wait, why is this a different example? It's the same thing. Basically you just call the same thing, just it's a different example, and you have two things that implements the same thing. Notice here, in this case, when you call fly, if you have a human, when you call fly, Rust doesn't know which one is, are you calling pilot or are you calling wizard? Because you have both function fly. So Rust doesn't know, but this is a different example. The error is similar to this. So boom. Mushin, there you're already dead.
Nani?
Oh. Okay, now it works this time. Okay, thank you. Yeah. So basically the compiler bombed already. Then to solve it, now we need to use something called fully qualified syntax. Now you need to do this, type as trait and the function. So this is also this is the same example of the error one. Basically you have this dog as animal. So the animal is a trait. So you are using the type called, the type is dog as animal. So you run the animal within the type dog. So you run this baby name. So you can know, okay, which trait within that type is being used to specify exactly which one, because one type can only implement one trait at one time. And yeah, there's quite a lot, I think. And the next is coherence. So it's discussed in one of previous talk. Basically, it means that there is at most one implementation of a trait for any given type. For example, there's a cert. Cert is a popular Rust library for serialization and deserialization. Basically, you do the JSON, you do YAML, JSON, CSV, those kind. kind of conversion, convert it to a serialized format. Some other languages call it marshalling thing. So there's a serialized is a crate, and you have another crate. You have a duration there. So both of this is not your crate. So you can't do this because this is not allowed in offline rule. You can't just like I mentioned before. You can't just implement a trait for other people's stuff. Like you can't just randomly go and implement this for other people's stuff. If let's say there are like multiple crates, and then different people randomly go and implement the same trait for the type, that it will break. It will randomly break. Then it's like suddenly it will be very surprising for other people. Hey, how come when I add the crate to when I add another crate to use, like basically use another library, then suddenly existing code break. So yeah, Rust doesn't allow that. So you can't really do this due to orphan rule. So one way to solve this, so this whole thing is called coherence, and most one thing, or also called orphan rule. And so one way to do this is to pick it the original struct into one's own crate, like basically you duplicate. And the last thing is module confusion. You notice that the traits just now we see is imported as the like normal types. Just like I'm also confused, like, oh, full is it a trait, or full is it a struct, is it a trait or enum? Because it could be any of them. But so usually to these people do is people usually will put it as like action, like you see serializable sort of an action or something, or add, or like iterator sort of action, not like this noun thing. So this is a normal use. Normal import, you import from standard library, fs, the file system. Is a normal struct, and then you use the standard library, the IO import output, the buff raider. Buff raider is a buffer, which means that the raider is there's a buffer for it. So you don't need to it's backed by the memory. So you don't need to like keep issuing the system call. And then there's also rate. Rate is a trait. So you notice here, it's not noticeable, like buff raider is a type and rate is a trait. And if you didn't include the trait here, this function won't compile, because you need the rate trait to be able to run the function rate. This is an extension trait because it will put this function in scope. If you don't have this rate, then you can't do this. You can't run the methods within the trait. So that's why I say the first thing I say is it needs to be in scope. So you wrap the buff raider new, you open the file and put it around the buffered raider. Then you have a buffer. This is basically an array of 10 zeros. It's just mutable. You can change. Then f.rate, you open the file and you rate into the buffer. Here, rate into the buffer. Can ignore this for now. This means mutable reference type. You pass in as a reference, but can be mutated. Mutated means you can change the value. And a question mark basically means the error handling in Rust. You propagate out. So print out, and here it will print out the bytes. It will print out the bytes within the buffer. So basically you see this. So if the trait is not here, and you notice it's not, you can't. The people say this called no grabbability. You can't grab for the rate. Grab is like you search. If you like, let's say sometimes you search file, you can find file here. You search buff raider, you can find buff raider. But you search rate, oh, you cannot find any rate. Yeah, what is this? Yeah, so if you remove it, then this will break. Yeah, there's no grabbability. Or you can just use this prelude. But if you do prelude, the star, you don't know what is in the star. So if you remove this prelude, then this will break. Yeah, so this is some sort of confusion that I noticed. So, okay, the end. There any question? Any question regarding crates, or anyone to see any examples can ask question? Hello. Any question? Anyone have any question? Should we end? Okay. Come. If there's any question, yeah, can just open the mic and ask. Font size I already increased. Okay. Okay. Hopefully you all can understand. So for the Rust meetup, we will have it every 2 months, and usually there will be a topic, and anyone can give the Rust talk, and yeah, speakers are welcome. And then thanks a lot for joining. Up to you all to see, and if you all want, can ask question, like can ask, like show a demo or something. But yeah, this time I didn't do a demo. So okay, thanks a lot everyone for joining. Yeah, can end the screen now.